This webcast continues Worksheet 3C, where we're talking about stacks of kinematic graphs. So this problem is, I think I've labeled it number 5 actually. Okay, so first I'm going to do this scenario on the left-hand side. And so they're giving me a position versus time graph. And I can see that this object starts at some positive position, right? It's above the origin. It first moves at a constant speed in the positive direction. I know that because it's linear, so the speed is constant, and it has a positive slope. So it's moving in the positive direction at a constant speed. Here, where this dashed line is, it turns around and it moves in the negative direction now at a faster speed. I know it's faster because the slope of this negative line is steeper than the slope of this original line. Okay, so let's show the velocity versus time graph. The velocity should be the slope of the position versus time graph. And so first I had a positive slope and it's constant. And then after it turns around, I have a constant negative slope, but the value of that negative slope is bigger, right? It's steeper, so I've got a bigger negative value here than I had the original positive value. Now, for the acceleration, there really is no acceleration in this scenario. In both directions, it's moving at a constant velocity, and so the acceleration for at each point in time is 0 because the velocity is not changing. And then we want to show a motion map for this scenario, and so I'm going to show the velocity vectors on top and the acceleration vectors on the bottom. And so it didn't start at 0, it started at some positive position. I'll just put it here, and it's moving at a constant rate. I don't know what it is, so I'm just going to choose 1 increment per second. And so I'm showing 3 seconds of motion in the positive direction. Girls, please try to show at least 3 seconds of motion for each portion of the trip. I know that these graphs are descriptive. They're not really quantitative. They're not giving us the amount of time and data that we can use to calculate the specific velocity. But by showing 3 arrows for that first portion of the trip, it's easy to tell whether the arrows are staying the same, like they are here, or whether they're getting longer or shorter. Okay, so it's moved in the positive direction, and now it turns around and goes in the negative direction. So in my motion map, I have to move up a level, and it gets faster. And so instead of having just 1 meter per second, I'm just going to make it 2, And I'm actually going to just extend my scale a little bit so that I can do that. So I do not show any dots stacking, right, because it did not pause here. It just turned around and immediately started going at a faster speed in the negative direction. And now let me show the acceleration vectors. First, I put the position dots in the same places that they were up above. And in this case, acceleration is 0, so I don't have any acceleration vectors. Okay. The description here, and I typed this just to save time, I always want to say where it begins. So here it began at a positive position. It was not at 0, not at the origin. It began at a positive position at time 0. The object moves at a constant speed in the positive direction. Then it turns around and moves at a faster constant speed in the negative direction. Okay, let's do the next one. So here they're giving me again the position versus time graph, and I can see it's not linear. It starts out, and I like to put little tangent lines. So at the beginning, the tangent line is fairly horizontal, but at the end, the tangent line has a fairly steep slope. those tangent lines give me a sense of the velocity, because remember, the velocity is the slope of the position versus time graph. So at the beginning, the velocity is 0. It started from rest because the tangent line was horizontal. At the end, the slope is some fairly big positive number, because look at my tangent line, and it has a steep slope and it's a positive slope. So the velocity is becoming increasingly positive for this object. Okay, so now let me show the acceleration versus time. Acceleration is the slope of the graph above it, the slope of velocity versus time. And this velocity versus time graph is linear, and it has a constant positive slope. So the acceleration is a horizontal line at a positive value. Let's do a motion map for this. So again, it does not start at the origin, so it starts at some positive position, and it starts out very slow. It starts from rest, and then it gets faster and faster. And so I should see the velocity vectors getting longer. And then let's put in the acceleration vectors. I start by putting the position dots at the same place. Here, the velocity vectors are getting longer. It's speeding up, and so acceleration should be pointing in the same direction as the velocity. But remember, I make the velocity vectors all the same length because we're looking at situations with uniform or constant acceleration. And the description for this would be: beginning at a positive position at time 0 seconds, the object speeds up as it moves in the positive direction. Please use the words speeds up, or, if it's slowing down, you can say the object slows down. But use these words. Talk about how the speed changes rather than saying the object moves in a positive direction at a constant rate of acceleration. Because to a physicist, acceleration can mean either that the speed is getting faster or that the speed is getting slower. And the simplest and most efficient way to describe that in words is to say either it speeds up or it slows down. Let's look at a couple more here. This is 7 and 8. Okay, so in number 7, I can see that the object is moving in the positive direction because generally the slope is positive. It starts at a positive position, but look what's happening to the slope. If I drew some tangent lines just to get a sense of it, it starts with a tangent line that has a positive slope. So it starts moving with a positive velocity, and at the end, the tangent line is horizontal, which has a slope of 0. So this thing is slowing to a standstill. The velocity is always positive because it's moving in the positive direction, but as it moves, it's slowing down until it's not moving anymore. The acceleration here should show the slope of the velocity versus time graph. Well, velocity versus time is linear with a negative slope, and so acceleration is always negative, so it should be a horizontal line at a negative value. Let's show what this looks like in a motion map. So it does not start at 0, so I choose a positive position for the first position dot, and at first it's going fairly fast, but then it gets slower, and then it gets slower. So the velocity vector should go to the right since it's moving in a positive direction, but they're getting smaller and smaller because it is slowing down. And then I'll show the acceleration vectors. So since this object is slowing down, the acceleration vectors point in the opposite direction of velocity, and so it has a negative acceleration. And look, that corresponds to the acceleration versus time graph that we drew that showed acceleration at a negative value. So the description for this in words would be: beginning at a positive position at time 0 seconds, the object slows down as it moves in the positive direction. I can tell it's slowing down again because the slope is getting less steep, the slope of position versus time. Okay, let's look at 8. So here I have an object. For the first few seconds, the position's not changing, so it's not moving. I know that means the velocity is 0 for the first couple of seconds. Then it's moving in the negative direction. I can tell that because the position is getting smaller. Generally, the slope here is negative. That means it's moving in the negative direction. I'm going to put a couple of tangent lines here so I can see what's happening to the velocity. Velocity starts at 0, and then it becomes steeply negative, so it becomes a big negative value. So this is what's happening to the velocity. It's very important here that the velocity be at a value that's less than 0, because this object is moving in the negative direction, and the sign of the velocity has to match the direction of motion. Okay, now let's show the acceleration versus time, which should be showing the slope of the velocity versus time. For the first part of this, the velocity is 0 and it's constant, and so the velocity is not changing, and so the acceleration is 0. For the second part of the trip, the velocity is getting more and more negative, and I can see that it's a line. The velocity versus time graph is a line with a negative slope, so the acceleration is negative. Okay, so we have something that is staying still for a few seconds, and then it speeds up in the negative direction. So let's draw that. So I'm going to draw something that's staying in the same position for 3 seconds, and then it starts speeding up as it goes in the negative direction. So the dots, the position dots, stacked on top of each other while it was not moving, and then when it started moving, they're moving to the left in the negative direction. My velocity arrows have to point to the left, and they're growing. They're getting longer because it's speeding up. For the acceleration, first I put the position dots at the same positions. For the first 4 dots, I don't draw any acceleration vectors because the acceleration is 0. And then it's speeding up in the negative direction. When something's speeding up, the acceleration vectors point in the same direction as the velocity vectors. In words, the description for this would be: beginning at a positive position at time 0 seconds, the object remains stationary for a few seconds, then it speeds up as it moves in a negative direction. Okay, let's do a couple more here. In number 9, I see an object that is moving in the positive direction. You know, its position is getting bigger. For the first part of the trip, the graph is curved. It's parabolic, so it is speeding up, right? Because I'm going to do a couple of little tangent lines, and I can see that the slope, which is the velocity, is getting steeper. For the second part of the trip, look, the slope is not changing. This tangent line and this tangent line have the same slope. So it is moving then at a constant speed in the positive direction for the second part of the trip. So the velocity started at 0 because I have a horizontal tangent line, and it gets faster. And then it stays at that fast positive velocity for the rest of the trip. The acceleration is showing the slope of velocity versus time. So for the first part of the trip, the acceleration must be a positive value, right? Because the slope of the velocity versus time is positive. For the second part of the trip, there is no acceleration because the velocity is not changing. Let's show a motion map for this. So it starts at position 0 and it gets faster. So it starts out very slow and then it gets faster. So I see my velocity arrows pointing to the right and getting longer. And then it stays at a constant velocity, and I'm running out of space, girl, so I'm only going to show 2 arrows, but it shows a constant velocity for the last part of the trip. For acceleration, for the first part of the trip when it's speeding up, acceleration points in the positive direction. And then for the last part of the trip, the acceleration is 0 because the velocity is not changing. In words, I would describe this as beginning at position 0 meters at time 0 seconds. The object speeds up as it moves in the positive direction. Then it continues moving in the positive direction at a constant speed. And I think I'm going to go down and do one of these for the last one, since this video is getting long. I'm going to do number 12. So here we have this object. It begins at position 0. I'm going to do a couple of tangent lines. I can see that its velocity begins at 0. This tangent line is horizontal, so it's starting from rest, and then it is speeding up as it moves in the positive direction. Then it keeps going in the positive direction, but look what the tangent line is at the end. It's horizontal again by the end, which means a slope of 0. So here the velocity is getting more and more positive, and then it's returning to 0. And so the acceleration versus time should show me the slope of velocity versus time. So for the first part of the trip, acceleration is positive, and for the second part of the trip, acceleration is negative. Let's do a motion map for this. It starts at position 0. It starts very slowly, and then it gets faster and faster. So this is the first part of the trip where it is speeding up in the positive direction. Then it starts slowing down. It's still going in the positive direction, so the arrows still point to the right, but now they are getting shorter again. And then if I were to show the acceleration versus time, or the acceleration vectors on my motion map, for the first part of the trip, when it is speeding up, acceleration points in the same direction as the velocity vectors. But for the last part of the trip, the acceleration turns around and points in the negative direction. And so the description in words here would be beginning at position 0 meters at time 0 seconds, the object speeds up as it moves in the positive direction, then it slows down to a stop as it continues moving in the positive direction.